So welcome to this last session. Is it the last session? I think it is, right? Last but not least, refactoring to a system of systems. My name is Oliver Gierke. I work for a company called Pivotal. You probably heard of that. I always have to say that because in other countries, some people haven't heard about Pivotal. I'm leading the Spring Data projects there, which means that everything that's sort of data access related in the Spring Framework ecosystem that's not directly supported by the core Spring Framework is sort of crossing the desk of my team, basically. And as you might know, the Spring Data project mostly consisting of a repositories abstraction in on the highest layer, that's probably it. That sort of gives me the connection to some DDD topics and then some interest in RESTful APIs, hypermedia stuff, then sort of blends it into the topics of software architecture. And what I'm going to do in the next couple of minutes is basically have a look at some implementation of monolithic applications, typical monolithic applications, in this case written in the Spring Framework, but I guess the patterns we're going to identify are also present in, like, let's say, non-Spring applications. I'm not sure why any of such things should ever exist, really, but just kidding. So we want to identify the patterns that are actually used within these monolithic systems, and especially focus on the interactions of bounded context. So I'm assuming quite a bit of like pre-existing knowledge, not too detailed, but basically different parts of the systems that are supposed to be isolated from each other and still need to interact with each other, right? So there's some patterns in there, and how do people usually implement those? And actually also have a look at some of the technical means that the Spring Framework provides to ease these kinds of interactions, right? And then we want to take a look and see if you just go ahead and come to a conference like this and learn about microservices, and then again go like back to work to your team and then have learned, okay, we need to split up that thing into different systems, and then you start doing that and basically keep the same interaction patterns around, right? And what that actually results in, and what that results in is usually not pretty and complex and complicated. So we want to have a look at the negative effects of a split up of a system if we just translate those patterns one-to-one. And we then want to take a step back, actually, and have a look at how we can actually improve the monolith first, right? So what can we actually do to build maybe a better monolith? How can we improve that? And then actually, that's the thing. And then have a look at, okay, how do these improvements affect a potential split up of the system, and how do we actually get to a better version of a split up system? I try to refer to that system of systems term better than the term microservices, because that seems to imply the latter seems to imply some focus on size of things, which I really think people get too much carried away with, but rather, okay, we have these systems interacting with each other, and how does that actually work, right? How do we like translate these new concepts into a distributed system? And hopefully we're going to get to that, two different approaches of integrating these now like co-located systems. One's using messaging, and another way of integrating is basically a REST-based approach, and I think especially the latter is kind of under-focused on, so often people don't really have that on the radar as an option, so we're going to look into that. All right, so there's some sample code I've provided. So each of the big green bullets that I had has a sample project or multiple sample projects backing them. You find them in my GitHub account under the SOS, which is a kind of a neat abbreviation for that. In the repo, yeah, and let's have a look what we're going to build. So I was kind of like trying to come up with some example that's not like too simplistic, but like simple enough so that it actually allows us to reason about. So the idea I have is I build a typical e-commerce application that consists of a catalog, contains products, product details, and prices, of these products, right? They, of course, vary over time. The descriptions change. New products get added, what have you. So we have a kind of orders part of the system that accepts orders from customers. These orders consist of line items. And we have an inventory that keeps track of the stock of these individual products, right? So inventory items. So that's the kind of situation that we find ourselves in. And I'm going to have a look at like 2 key use cases here that we're going to see how the implementation varies in these different kinds of architectures. First thing is when I add another product to the catalog, we need to somehow initialize the inventory, right? So we need to basically register a zero stock for that particular product. And the other thing is that whenever a customer sort of completes an order, we sort of have to update the stock, right? So the inventory. So for each individual line item, we sort of have to subtract the ordered amount from the stock that's currently available, right? That sounds pretty simple, pretty straightforward, but can get interestingly complicated, especially in the like distributed systems scenario, really. All right. So the key questions I want to focus on, actually for each of the architectural approaches. Common design patterns, I already mentioned that. Interaction patterns that between the bounded contexts. Consistency is a big question, right? So what kind of consistency can we expect and do we deal with? And do these different architectures sort of require, right? So sometimes it's there's like different, usually strong consistency versus eventual consistency, and is there a way to avoid one or the other? Do we have to accept maybe eventual consistency in some cases, what have you? How do these systems behave in erroneous situations is basically the question, like especially if we distribute the system, what happens if one component within that system of systems goes down, and how does recovery actually take place, and how does that actually work, right? And actually I think almost the most important thing is usually people, or the primary business driver behind structuring in a system of multiple systems is that you want to evolve those independently, right? You want to get away from that big ball of mud because it's too slow to actually produce new features. Teams are basically stepping on each other's toes or have to wait for a big release cadence or what have you. So a lot of people seem to be very focused on building a set of microservices in the first place. Even worse, they sometimes focus on building a single microservice in the first place and how quickly they can actually do that, which is completely like countering the actual intention, right? You don't want to really focus on building the things in the first place, but how do you actually evolve them, right? There's no point in building 20 different services, one, and then going further and evolving them, changing them, right? So this kind of separated systems architecture is only reasonable if you actually can do that, right? So can change one of the systems without actually breaking the others. All right. So especially when you look at the example code, I'm like sort of like involved in the DDD space quite a bit. People sort of look at a different way on the code side, which is kind of weird. The example is really focused on the interaction patterns and how the different parts of the systems interact with each other. It's not a cookie cutter recipe for how to build things, especially when it comes to the like more design questions, right? So I have monetary amounts in there modeled as big decimals. That's probably not a good thing to do in a real world application. I just didn't want to spend time on then teaching JPA, what have you, to actually persist a monetary amount in value object that I might want to create in a production application, because that would sort of distract from the actual focus of the example, right? So I got that feedback on the sample code, that's why the warning is in here. So what does the monolith look like? So we have this kind of catalog thing, and in the example code I have prepared, it's actually pretty well organized compared to some other projects I see. So we have like packages per kind of domain or per bounded context. And the catalog has a product entity, right? It's a JPA entity. We're going to see that in a bit. And we have this orders package, which has an order entity consisting of line items. The line items refer to the product. Actually, they do that like within, I think within direct object reference, which is already questionable, I guess. And we have the inventory where the inventory item entity sort of points to the product. And the interesting bit that we're going to look at in a second is whenever an order is completed, actually the inventory is updated by the order management, basically triggering some functionality in the inventory. So you see some semi-structured domain model here, an aggregate really in each of these packages. The structure is actually pretty decent, right? So let's have a look at the code here. So I actually want to just have a look at the use case of completing the order, right? So you have this order class here. A lot of JPA gibberish that you see, nothing fancy. It's actually, there's an order repository for it, a Spring Data repository that you see, and that's just like keeping the line items in here. And the line item, let me check. Yeah, so we even have a direct or reference to another aggregate in the order aggregate here, which can of course argue that you'd want to rather just only keep the product ID around and maybe some replicated data like the description or what have you. I just decided to keep things simple here, to have the product reference here. All right, so what does the order manager do? There's a transactional, yeah, that's the wrong one, is it? Monolith, no, I want to go here, this one. So it basically changes the state of the order and then triggers the functionality in the inventory and then persists the state of the order itself, right? So it's basically tweaking the aggregate, changing its state of triggering functionality, persisting the order again. It's a transactional method, which is kind of neat in this case, so it's pretty comfortable because you can actually change multiple things, right? You change the inventory, the state of the inventory, and you change the state of the order, and it's all strongly consistent, right? Because either the changes happen or they don't, right? That's like just a consequence of the programming model, the consequence of declarative transactions. That's pretty, comfortable for us as developers. So what is the downside of that basically is that it's very easy to just like get used to that kind of thing and then just go ahead and add more stuff to actually that method. Assuming the use case, we have some kind of rewards program so that every customer gets a, let's say, some kind of loyalty points or something for each completed order. You can go ahead and implement that new rewards program functionality completely separate, right? A separate team, what have you. But in the end, you will have to go place in the code. I'm sorry about your stuff. Can we change something about that, or is that okay for you guys? I hope so. To go back to this place in the code and trigger that new rewards functionality, right? So even if you can get the work separated on that new functionality, at some point you have to come back here. And that's kind of like, it's some kind of gravity in the code base that really makes explicit, or it makes it obvious that there's something missing here, right? Which is the event of the order completion not being modeled as an explicit concept, really. Right? It's kind of implicitly contained in that method here. All right. So back to the slides. Yep. So usually, I mean, it's what we have in the monolith example here, and which is kind of positive, is that we have separate. sorry about that. Separate packages for the bounded context. Again, okay, are we changing batteries or is there? Well, okay, whatever. So we have some way of structuring code and actually locating code so that it's easy to stay cohesive. We can even use, like in Java, use visibility modifiers in terms of like package scope to avoid things being used from the code base. An important thing that is often underrated is that the inter-context interaction is process local. So the inter-context interaction is process local, which means there's not a lot that can actually happen. The method either completes or it throws an exception. And oftentimes I feel like this kind of simplicity is, because we just got so used to it, is kind of underrated, right? It's actually the canonical form of exactly once delivery, right? So you invoke the method, and it either works or it doesn't, right? So there's no JSON marshalling going on. There's no network. There's no latency. I mean, not no latency, but no network latency, literally. So it's pretty simple, and it's pretty neat that it is just that way, right? So that's something I deliberately built in or I'm kind of like torn on it. So the fact that I'm referring to the product from the line item is kind of neat for refactoring purposes because I can change things easily just using my IDE refactoring tools. On the other hand, we create some kind of coupling between the two bounded contexts, which we might want to avoid, right? Avoiding that requires more indirection. For example, I have a product ID, then if I need access to the product, I have to look it up through some other API mechanisms or whatnot. So it's kind of like, it's a convenient thing to have because it allows me to change things easily, but it's also so some kind of drug or has like coupling downsides, basically. Right? Yeah, procedural implementation of the order management. You see, it's like going like it's kind of step-by-step thing, which means if I want to add anything to the process, I basically need to go to that place and then decide where to actually put the method call to that rewards management system that I might want to introduce. Right, yeah. That's basically what I had said. Well, what feature exactly, right. So an advantage I see in that kind of model is it's very easy to refactor, right? So, and the funny or the interesting aspect I think is that if we talk about evolvability and changeability, you actually have, while you still have a very coupled model, it actually, if structured properly, it gives you very good evolvability and changeability because you can use your IDE tools to refactor things, right? To move code around, to refactor the boundaries of your bounded contexts, right? So changeability is given if you structure it properly. Strong consistency is also very neat because it's easier to reason about it, about the code if you have that. On the other hand, as I said, it basically creates incentives to pull more code, to pull more changes to your objects into that transactional boundary, and then basically create these big transactional boundaries that you have to untangle if you want to split things up, really. What else did I just think of? Whatever, I'd probably get to it in a back. So yeah, also I mentioned that on the downside, we basically have to go back to that piece of code whenever we want to add a new feature to something that is sort of related to the event of completing an order. All right, so what can we do instead, even in the monolith? So suppose you have a system that sort of works like that. You could go ahead and oh no, sorry. We're going to take a look first at what does that look like if you basically just like decide to split up the system. So now the catalog bounded context is not a simple package within the very same Java process. It's a separate system. which means there's some interaction going on in terms of like the order system requiring access to the catalog system, right? And also to the inventory system, because it wants to basically tell the inventory system to update itself after an order has been completed. And the catalog is going to tell the inventory to basically initialize itself whenever a new product is registered with the catalog. Which means that we need some kind of active invocation mechanisms, which in the days of, or in the current days, is like HTTP requests mostly. And in this case, it need to be like POST requests, which is usually the worst kind of version that you can have in terms of like remote procedure communication, right? It's non-idempotent, it's unsafe. So whenever you don't, let's say you're implementing the order system, whenever you don't get a response from the inventory system, you're basically screwed, right? You don't know whether the request arrived in the inventory system or whether you just missed out on the response. So you can't really repeat that method. And even if it's just like plain GET requests, right? So if it's more like defensive interactions, you basically have to deal with a completely new class of error scenarios, right? You need to marshal the data into JSON. You need to like invoke that network request and then unmarshal the response and what have you. So, right. So what do people do when they now deal with like this kind of system structure where you basically have put a network in between these components? So we have challenges, technical or architectural challenges that have been induced by the style of distribution that we chose. What do people usually do? What do we as developers do when we face technical challenges? We add more technology, right? So people go ahead and say, okay, this stuff, so we need, the first thing we need is circuit breakers. Because like if the system doesn't answer, I don't want to do the post request immediately. So the question comes up, okay, but what do we do instead then, right? If that inventory system is not even there. So how do we actually promote the fact that the order has been completed to the other system if it's not there? Retries is the next thing, right? Retries, circuit breakers, and then people realize, oh well, like a post request that's adding quite a lot of latency, so we have to do that stuff asynchronously, right? And then they do reactive programming, and then it's like technical stuff being piled up on like different layers of technical frameworks being added on top of each other to basically solve a problem that's coming from some architectural implication or some architectural decision really here, right? So while this sort of like, I mean, sometimes it's not, you can't really avoid to do things like that, but I'd argue there's a different way to just like simply architecture your system in the first place to actually avoid that kind of scenario in a lot of cases. So to summarize the things, so the design decisions or the consequences of the design decisions here. One thing that's also often like overlooked is, okay, how do we actually know, make sure that we have some kind of consistency between the orders placed and the inventory and the stock we keep track there, right? So if the answer is there is none, right? So there's no local transactional consistency anymore. So we sort of, or the first reaction usually from people is, okay, then I need two-phase commit. Yeah, right, okay, that's not going to really work in a distributed systems environment. It already is a hard thing to, if you're just like dealing with messaging and transactional databases locally, it's kind of a challenge to get those to work together properly. If you like span like business transactions across multiple systems, that's going to be pretty horrendous. So we need to accept eventual consistency anyway. As I said, we're usually adding a lot of technical overhead, a lot of technical aspects that are all of a sudden creeping into what I was told, or people are told microservices is about like domain capabilities and domain functionality, right? So we center our services around business capabilities. And the first thing people do is go off and build a deployment pipeline with Docker and Kubernetes, and then they do Hystrix and whatnot. So it's all these kinds of these technical aspects sort of get a lot of focus, whereas the actual business is sort of kind of becoming some kind of, okay, by the way, we need to solve that business problem here. At least that's the feeling I get with a lot of developers, but that might be just my personal experience, right? So we need to deploy this, a lot of technology here to actually help out with the problems. And that I basically just made up an example where we call a single remote system. But if you start with that kind of like interaction, usually the call to answer a user request is not ending in the second system, but in the third system or a fourth system. So you're accumulating latencies. And I've been I said it at lunch, I think, the other day, with someone saying they completely gave up on Hystrix because it was kind of impossible to properly configure the timeouts they have for these different systems. Because depending on which system is calling which system, like the timeouts of the first one don't really match the one. There's no point in having a timeout if the latter call is already timing out in the first place. So there's a lot of like extrinsic complexity or accidental complexity showing up that you really have to do. So yeah. Okay. Another issue that you have with these kind of systems is that you need to know the other systems that you're interacting with. Knowing means they have to be present when you run the system, right? Or you sort of have to at least stub them out, which makes testing the system more complicated, right? I'm basically made up a small example with just one system interacting with a single other system, but assume you basically create this kind of mesh of systems, then that quickly becomes quite a nightmare in terms of like, okay, how do I actually even test my business functionality? Of course, you will deploy means to like, okay, like this hexagonal architecture, so you can actually separate the code, mock out servers, like even to unit test your application components. But for integration testing, you actually need these other systems sort of running. And what I've also seen is a strong focus on trying to replicate the ways that you define interfaces like locally for components that interact within the same JVM in that distributed systems world, right? So the idea of a strongly typed interface and parameters that methods in that interface take, and like fleshing out all the details like enum values and whatnot, is exactly translated into like the remote interaction way. However, there's this really, really great talk by, I think, Jim Weirich about I think it has a weird title, like what is it, the answer to the universe and everything or something, where he talks about this concept called connaissance, which is a degree of coupling between two components that were sort of like, or have to interact with each other. And he has this kind of, or the summary of that part of his talk is basically, the more remote two parts that interact with each other are, the lesser the coupling you want, or the lesser coupled you want them to be, right? And it's definitely recommended to look that up, but it's really problematic to try to use the same definition concepts of interaction between two components that are born and raised locally, like let's say that these two classes and an interface within the JVM, compared to actually the two remote systems that are supposed to evolve implicitly, right? So again, this is usually also where this kind of evolvability of an individual system fails, right? So because if you can't change that one system anymore and without breaking others, then it's really getting complicated. Then you get into this kind of, how do I version my API kind of discussion, and things just go downhill from there. Right. All right. let's take a step back to look at the monoliths, or an idea of how we can actually structure or build the monolith in a slightly better way. So the idea is that we sort of keep the same things around, right? But actually only change the interaction pattern here. So what we focus on now in terms of modeling and in terms of like also the implementation then is the events that the individual bounded contexts actually produce. So let's say the catalog is producing a product edit event. The orders system is of course depending on the products, but at the same time producing like order completed events, right? The inventory also still has that coupling to the catalog because it's kind of like still referring to the products, but at the same time it sort of subscribes to the events, the order completed event to find out about like orders completed, and to the product edit event for that initialization use case basically. So what then basically happens is that there's some kind of infrastructure that publishes the events to the inventory, and we're going to look at that in a second. And then in turn, the inventory might even produce events on its own so that we can then maybe have a new or implement a new part of the system that still lives in the same application, but then can actually react to these out-of-stock events and then trigger some purchase or what have you. Let's say I ordered 5 TVs and we only had 5 left, so then we want to restock, basically. Right? So what the fundamental principle here is that we sort of invert the dependency. It's a different kind of dependency inversion, really, between the bounded context. So whereas beforehand, the order subsystem was directly invoking the inventory, it's now only publishing the events, and then the event publication mechanism is sort of taking care of publishing that event to the interested listeners. So I guess you might be like, a lot of people, when I speak about events, I deliberately spoke about events, not messages in the first place. People like think about messages in the first place. So when I say event, you hear messages. But at the same time, there is actually a very simple mechanism in Spring Framework that, where is the monolith? There we go. That allows you to send, it's called application event. Who would have thought that? Right? So there's some abstraction in Spring Framework that you can use to publish these events. There's the application event publisher. That's a component which the application context invokes or implements, and then you can inject that application event publisher into your code and then like use that to manually publish events. However, there's some smarts in Spring Data actually that we've like shipped a couple of versions ago that make that publication of these events even easier. And so let's say if you only know about application event publisher, so it's kind of final application event publisher, this one, you'd have to inject that thing into your application component and then say basically publisher dot publish event, and then you say order completed event. It doesn't. Yeah, it's funny because I actually hide that in that order class. So you'd basically go ahead and say new my event. You publish that thing here, right? So that's the way it works with plain Spring means, which is kind of neat because then you can have application listeners that either action or on transaction completion receive those events. But that's still, I didn't really quite like that because it actually makes our business code dependent on infrastructure components, right? So this application event publisher injection, this one here, I didn't really like that. And the other aspect of that being, it's sort of now the service's responsibility to actually create the event and publish it. Whereas actually, like, if you follow the blue book, it's about like the aggregate sort of producing the events, right? And the idea we had was that, okay, we could, and again, aggregates and repositories sort of being the domain of Spring Data, we basically thought about, okay, what if we provided some means to go ahead and actually, in this case, these two annotations on your aggregate root class to allow you to register the events that some certain business use case actually causes inside your aggregate root, and Spring Data then actually taking care of publishing these events whenever you actually run persist that aggregate, right? So what we do here in order complete is we basically change the state of the order, and at the same time we keep the events we have around and then basically add the order completed event here. And that just changes the state of the aggregate, and once the aggregate is saved, it's sort of the event is published through the standard mechanisms, right? And then on the reading side of things, we basically just go ahead and say, okay, we have an inventory listener. It's an add event listener with the order completed event, and then we do basically the stock update here, right? So there's no dependency from orders to inventory anymore. We've inverted the dependency from inventory to orders, right? And that's still, the nice thing about that is we can sort of get the benefits of the decoupling, right? The event-based interaction here. We still, however, get the same transactional semantics, right? Because that event listener is executed within the transactional boundary of that method. It's transactional because it's on the class here, right? So we get some kind of decoupling within the monolith in this case, and that would actually even allow us to, as I mentioned before, to add that rewards program kind of functionality in a separate package, and then still just deploy that listener and update the rewards, asynchronously. So we don't have to touch the code in that package, right? So it's pretty, gives us like a bit of decoupling, also team decoupling, organizational decoupling if needed. We still code on the same code base. We still have to probably release together, so we don't solve that problem, but we get a bit of the benefits here. We had that. Yada, yada, yada. Animations for the win. Okay. One very important thing, I think, is these events, the event creation is moving, the logic is moving to the aggregates, which is kind of neat because it just like aligns with what the fundamental idea is in the first place. We implement any kind of interaction between the bounded context is implemented using events that then can trigger some code and some state change in a different bounded context. We sort of invert the dependency, which is kind of a strong or like kind of a net benefit in terms of like the ability to add new functionality to the code base, because we sort of don't make the order management bounded context that God component that has to basically orchestrate all the things, right? Here's the slide version of what I just shown you in the code base. So we basically have, there's some annotations and that abstract aggregate root class that sort of allows you to actually build or capture these events within your aggregate and then automatically get them published when you hit repository save, right? Yeah. So yeah, and the interesting aspect actually about that step being, you can now go ahead if you just like sort of flip the switch to that kind of event-based JVM internal event-based model, is that you can now be very selective and think about, well, that order completion event, that might be something some other system is interested in, right? So we can go ahead and just write an event listener that then publishes that event to whatever message broker we use, right? So we can selectively externalize those events and sort of start getting our hands dirty with this kind of like messaging integration with different systems, right? So, right, yeah, that's what I basically showed you. In the interest of the time, forwarding quite a bit. Okay, so we have this kind of improved monolith. We now already use events for our bounded context interaction. What does the split up of the system actually look like? So we have two big integration options for like different systems. One being like the classical messaging approach. This is what people usually even think about when I say events in the first place, messaging. And the other sort of underrated version of that being a purely RESTful implementation of event integration. Again, a bit of a focus, especially when comparing the two, I like to put on the focus on, okay, what do I need to run one single individual system within that system of systems? What happens if one of the systems goes down, right? Can the other systems like continue to work? What if a failed system comes up again? So how do we keep up with the stuff that happened in the meantime? And what happens if a new system enters the scene, right? So let's say we deploy this rewards program system, we implement that as a separate system, and we want to add that to the overall landscape, and then how do we actually get that to work? Okay. First option, messaging. So what do we do? I mentioned that before. What you usually do is you put a big message broker in the middle of everything. Right? In this case, in the example, I chose Kafka in the example in an embedded version, and then you have the individual systems publishing messages, the events as messages into that message broker. And the same for the orders, also the order system. No, the product edit. Oh yeah, good point. I was puzzled by that arrow, but right, it's a good point to mention. So as we want to decouple the systems, right? The question sort of comes up: how does the order system even know about like the current product descriptions, right? So we don't want to have any direct dependencies anymore between the interacting systems. So the order system sort of has to keep some kind of replicated data of the catalog information, exactly the parts of the data that it's interested in from the order's perspective. So that's probably the price of the individual item and let's say a description or something. So the order system has to listen to that event. It itself also publishes events, the order completed event to adhere to our scenario, which the inventory system is then sort of listening to. It's also listening to the product edit events because it needs to initialize the stock, as we said before. It's then publishing events in turn so that we could add this imaginary new system of that sort of reacts to the out of stock event. So you see everything is sort of centered around that message broker in the middle, which I find kind of weird in the first place, a weird idea in the first place, right? So we started with the fundamental assumption that we want individual systems individually evolvable, and we want them to be runnable like in a self-contained way, right? No shared state, and didn't we initially say share nothing architecture is a thing in microservices, right? But now we share this thing in the middle there, right? So it's kind of like, to me it feels a bit like not really counterproductive is the wrong word, but it's slightly subverting the original architectural idea, right? So we have this broker in the middle, which also means that we sort of move a lot of the configuration or a lot of decisions that are actually core to an individual system decisions that we make for those is living in that central component, right? So how long do we want to keep these events, right? Do we want to keep product edit events for like 2 weeks, for 2 years, for forever, basically, forever, ever? Yeah. So that's kind of it's not. I mean, it's probably not a problem to actually do that. But you basically put all this knowledge from different systems into that single place. And it also kind of begs the question, okay, I mean, you usually have, as it's a centralized component or a central component, you need to run that in an HA fashion, but still there is the risk of one of the systems going basically rogue and then flooding the broker with messages, and that might affect other systems, right? On the other hand, technologies like Kafka are really built for scale. There's been this article from New York Times recently where they basically changed their architecture to actually move to a broker-based architecture based on Apache Kafka. And so if there's the need for, if there's high volume events, you need really tiny eventual consistency gaps. That's probably a good solution for that. Right? Events as messages, that's what I said. What you have to like be, or one reaction I often got is like, okay, we have these events, which I think of as messages. We've always had in the Java space, we had like JMS, for example. And then there was AMQP coming around, RabbitMQ, and now like Kafka is a bit a new player in the game. There's like certain characteristics of each of these technologies and design choices that sort of imply some consequences on what things work and what things work which way, especially in terms of like how do systems find out about messages, right? So with JMS durable subscriptions, you can actually make sure that if a system has initially registered with the broker, goes down for a while, the messages pile up in the topic, or this basically in the subscription, and then if you rebootstrap the system, you basically get all the messages that have happened like in between the shutdown and the restart. However, if a new system enters the scene, you only see messages as of that point, right? So as of the initial registration with the broker, which is kind of, I mean, might be acceptable. However, we've worked with the customer that basically built that kind of reward system for their orders, and they were using the RESTful approach that I'm going to show you in a bit, but it was a really, the idea was, okay, we have order information of the last 3 to 5 years sitting around in that particular system. Why should we bootstrap the reward system and basically let every customer start from scratch, right, from zero? They already like spent like 2 or 3 years with us. Wouldn't it be cool if we could actually like just see or use that old data, that old orders history, to basically pre-fill their rewards, right? So that they don't start with 0 loyalty points, but rather with a couple of hundreds or whatnot. And something like that would be like impossible with a JMS-based approach here, right? Because you don't actually see the new messages. So assuming you implemented those order-completed events as JMS messages. The same for AMQP. On the fan-out exchanges, you basically get this sort of same behavior. With Kafka, it's usually the events, if you don't do anything else, the events live there forever or can live there forever. It's basically offset-based, so you can read the messages giving or telling Kafka, I want to read message from offset 4711, and then you get basically all of them. Yeah, just a difference in the way things work. Yeah, something I also see people underrate is the message serialization format. Yeah, we do messaging because we want to avoid breaking API changes in RESTful APIs. That's a statement I often hear, which is kind of like, okay, you're basically lying to your own pocket. If you want to, the messages have a serialization format. Usually it's JSON these days. But if you want to change something about that, you need to make your clients aware of those as well. And actually, with a message-based approach, you have to build something like content negotiation, something that you get for free in the REST world yourselves, right? So there's no mechanism for that. So pretty much every system has to agree on the serialization format, and then also make sure it's always up to date with the new version, right? And even with if you have like transactional databases or relational databases, especially in your system, then the question comes up, okay, that even the publication of the message basically requires a two-phase commit, right? Because, okay, you want to both commit the database transaction and the message being published to the broker, to have that transaction semantics, and that's kind of like complicating the picture already. So it's kind of, there's a lot of stuff that you get with the broker, but it's also not, it's not free of challenges, or you have these kind of like compensating messages flying around, compensating actions. Okay, let's have a look at the example. Actually, I've prepared for that before we go into the details, and I'm going to show you the hopefully interesting parts. And let's see if the demo gods are with me. That was we don't need that. That's the monolith. Inventory listener, there we go. So I have this thing prepared. Where is it? The SOS messaging. So there is a broker app, which is basically just that I don't have to deal with all these kinds of, with all the Dockers in the world. It's what is it? Spring Kafka, Spring Boot application that all it does is it runs an embedded Kafka, binds that to a port, and then actually has basically a broker running. Let me check whether we have this messaging broker. Yeah, it's still running. It's still running. I should probably shut that down for demo reasons. That's what happens if you try the demo before. And rebootstrap it so that we get a clean slate here. So we start the broker, and then I have my system that I had before split up into these three separate Spring Boot applications. And what happens is that we always have, or in each of the applications, we have an integration package that is basically, as I told you before, we're still using the Spring Application Events mechanism for the business logic in that app, and then have a dedicated class that deals with the fact that we want to publish the application event as a message to Kafka. And with like Spring Kafka, it's pretty much just a matter of getting a Kafka operations injected and then basically marshalling the product edit event as JSON in this case, and then I just like publish it to the product's topic. That's the thing here. So how do I actually react to in the other systems? How do I actually react to these events being published? Looks pretty much the same. So we also use Spring Kafka here. Whoop. Let's do all, that should be fine. So we register a Kafka listener as an application and subscribe to a particular topic, products in this case, and then we bind to a payload here. That's probably a bit of a hidden gem in Spring Data, actually, to be probably moved over to Spring Framework. But what this is kind of like JSON path-based payload binding. So I'm not using Jackson on the reading side of things because I want to avoid, or people usually then get the idea of, oh, if we have this product edit event in one system, we could probably share the code to use the Jackson unmarshalling, so they couple stuff together quite a bit. But what that does is it's basically taking the JSON payload, and we have just accessor methods here that we can then call. And what we get back when we call that method is basically that JSON path expression evaluated against the JSON payload. So we don't need to unmarshal all the entire document. We very selectively just pull out the parts that we're interested in. Right? It also allows us to basically say, or to have multiple JSON path expressions here, so that in case that the payload format changes, I can go ahead and say, okay, if it's now under product name, what would happen here is that the first lookup would try the product sub-document in the JSON to actually find a name property within that. And if that's not present, or if there's null in there, it would basically try another one. So it's kind of a very lenient way of looking up stuff. I don't need to touch any client code because I still just call that get method name. But yeah, that's basically what's happening here. We use a Spring Data repository to look up the inventory item by product ID, and then we initialize or we create a new inventory item with a zero stock. Right? And the same for when an order is completed. I basically just go ahead and have, what is it here? I basically pick out the line items and map that to a nested object called line item with a get product number. So there's not even a class living in this system for that. Just some kind of view onto the message, right? And we pull out the parts that we need and then basically update the inventory item with some quantity here, which then, what does it do? It finds the product and then decreases the amount in the repository. So pretty straightforward. I could actually try to run that so to see, actually show that to you. It's the example has a bit of a REST API put in front of these applications, right? So mostly for interaction purposes here, which I can have a look at here. It's like HAL browsers. That's a bit of a HAL is a hypermedia format in JSON that basically exposes or allows you to link or have links in your responses. So what you see here is, this is the, what is it? The product, this is the catalog, this is the inventory, and this is the order system. What I basically can do here is create a new product, saying, what is it? 300 iPhone X, Apple. Again, right, this is kind of like BS, kind of, because it's not a real monetary amount. So we've created the product in the catalog. So assume there's some kind of really nice web front end to actually do that. And that has now published a message to the Kafka message broker, so that we have we can actually look at the inventory items, and you see that it has created an inventory item with exactly the amount of 0 here, right? That's kind of the thing. If I have some functionality in the order system that creates a new order with a randomly picked product, I can do that and basically now find an order in here, right? An order with, let's say, the first chosen product that was basically in there. Oh, that's probably a good thing to show. How does the order actually find out about the product information? Yeah, it's basically, where is the product listener? There we go, right? So the order system also adds or listens to the product edit event. So when I originally added the product to the catalog, the order system goes ahead and sort of creates what it calls a product info from the product number and the description and the price. Right? So there's some kind of mapping between the different domains going on, which, I mean, the fundamental idea here is that to actually, for the customer to, it would basically say, order 2 items of the product with the ID 4711. And we want to avoid having to reach out to the catalog all the time to get the current product information. So we basically listen to the product edit event. We listen to the product details changed event of the catalog and basically create an asynchronously maintained replica of the product data. Exactly that part of the product data that we're interested in the realm of the orders, right? So there's no reaching out, no REST calls going on between the different systems. It's all message based, right? We've ordered 2 iPhones. That means we should have a negative amount of iPhones now in our stock. Also something that's kind of like reaching into the realm of consistency, right? If you think about the domain with like strong consistency in mind all the time, you basically say the amount of items in the stock can never be negative, right? Because physically it can't. However, usually we basically accept the fact that we sort of overdraw the number of goods we have in our inventory, and I think we should see that somewhere in in the yada, where is it? Where's the console? There we go. Yep, that's that one. Messaging broker, inventory. Yeah, in reaction to that overdraw, the inventory system basically produced a new event, the product out of stock event, just because we basically reached that zero stock, and published it to the message broker in turn. Currently, nobody is really reacting on it, which is probably problematic from a business point of view. But it basically shows that you can just like produce these events that might be interesting to someone else, and it's not necessary that you have that functionality that reacts on that event already in place, right? You could pick that up later on. Where do we want to go? Yeah. So, how do you actually build something like that with a purely REST approach, and why would you actually want to do that? What are the advantages, and maybe what are the disadvantages of doing so? So the idea that we sort of have is we want to take that shared nothing thing to the extreme and want to avoid that central piece of infrastructure here, right? Let's just as a thought experiment, what would we have to do then? So the idea is that we still produce those product edit events, but now totally change the way we actually implement the idea of publishing an event, right? So we're not publishing in terms of sending that thing somewhere, but just like registering it within the state of our system, right? You can very easily just like, and I've seen that being done successfully in a lot of projects, just either go ahead and just like persist that event into your local database and then have some kind of CQRS event sourcing mechanism to reconstitute the aggregate state, or you could just like even stay, let's say, more traditional and have your JPA entity product being persisted to the database, but at the same time, you just create another entry in the database that's sort of registering that event, right? So we have product X edit, what have you. And then you go ahead and basically just create a HTTP resource that exposes all the events that have happened to the system. So you basically make the event some kind part of the state of your application. And there's actually quite a bit of support in technologies for that kind of idea. But just like let's take the ideas to an end first. So we do the same for the order system, right? So there's some kind of pattern that we go ahead. We publish the events as local application state. We have an API for that. We have the same for inventory. And the client system, actually the subscriber of these events, now goes ahead and has some kind of separate piece of code within the application that periodically polls those APIs about changes, right? It basically knows about, okay, I've received the events like 1 to 4711, and then it basically can go ahead and say, okay, give me all the events after 4711. You can have that kind of cursor style, date-based. There's a lot of options to optimize on that, right? You can schedule or change the polling times whenever you realize no new events have been published for quite some time, so maybe I'm not like polling the other system like after every 2 seconds, but then gradually increase the polling delta here, right? So, and that basically just like works as a general mechanism. You can then go ahead and like have an API published in turn, and then that other system is basically polling on that, right? So how does that, I mean, the fundamental idea is that we consider events part of the state of that individual system. So there's a couple of things that you typically see in there, and in the course of preparing the example, there's been some kind of shared code that I thought might be reusable here, is the way you model the events to be able to just ask for the events of a certain aggregate, right, where you know some kind of identifier of, let's say, give me all the events that are related to orders, right, and basically filtering mechanisms. interestingly, or the HTTP as a specification gives you a lot of the things to optimize on this kind of interaction, because of course it's now load on the network, but and say HTTP caching is just a very, very great opportunity. Conditional GET requests are a great opportunity to avoid like data to be exchanged in a lot of cases when nothing has happened really, right? And of course pagination. If you just like have a next link, I've heard about like another company completely just reserving when the subscriber basically asks for events of a certain type in the first place, it just sticks to that. It gets a resource assigned, dynamic resource assigned, where the new events basically appear, and whenever there's new events coming up, there's like just the default next and prev link relations used for the client to actually to navigate through the events. That's kind of neat. Surprisingly or not surprisingly, this kind of idea of event lists or collection of things is something that's been like around in the web world forever, sort of. So atom feeds are very commonly used media type to actually expose those events, right? Because it's a standardized format. It's really easy to use, to produce. And the funny thing is actually or that one project that I know of that uses exactly that kind of style and using it very heavily, they really got used to and were kind of neatly surprised by the idea that you could sort of put an ear on what's going on into your system by using a bloody feed reader. Right? So you can just like, you don't have to actually build a system or look into some kind of broker-based console, but you just like add the feed URL to your feed reader, and then you just like see the stuff flying in and can look at stuff. So yeah, the example I have produced uses HAL, and there's also collection JSON for that kind of stuff. The point I'm trying to get across is there are standardized formats for representing a list or a collection or a feed of things, and it's a neat idea to actually use those, because then all the tools that you find that support that individual format actually work out of the box. Just I've used the HAL browser here, right? Yeah, so that's kind of the idea. We sort of get, and that's an interesting aspect, I think, we get the subscribing system to be in control of changing and analyzing the consistency gap, right? So basically the polling frequency decides how fresh your state is. I've seen that being used in cases where, let's say the inventory is under heavy load for whatever reasons anyway. It can easily decide to basically not consume any events anymore, right? So, and it can do that by just like, having a dynamic polling frequency built into the system. So there's more autonomy to the subscribing system. It's more self-contained, I guess. Right? Yeah. That's just an implementation detail. So to basically compare that to the other approach before, is first of all, we don't need any other additional infrastructure component, right? It's HTTP, it's the web basically across the board. So which event publication is becoming pretty easy, because we don't have, especially if we deal with transactional resources in our own system, we can just like persist another entry into the database, and there's no additional complexity in terms of like I have to orchestrate my local transaction with the message broker and what have you. So the individual system has control over how many events it stores, how long it actually keeps those around, right? So it's the system, the publishing system is very, very self-contained, and they don't even leave the system really, right? So that's kind of something going here. So we, of course, unless we really want to poll every millisecond, so because an HTTP request has some kind of overhead, we sort of have a bigger consistency gap usually compared to what you get with message brokers, Kafka, and what have you. Probably nothing for high volume event publications, but pretty well. The one thing I should have mentioned on the first bullet point on the last slide, testability is becoming much more of a non-issue really, because you can bootstrap the system, you can verify events being published by just like inspecting the local state of your database, and there's no need to have other interacting systems around, right? So it's kind of like you can, that's basically the fundamental idea of that, or the reason I kind of like this approach is that to serve a user request, you can build a system in a way that to serve a user request, you don't have to reach out to any other system, right? So it's kind of all locally replicated data. It's pretty performant. It's easily debuggable, right? If you have performance problems, you exactly know where to look. Whereas in a system where you have like one system calling another, and where does the performance problem actually come from? I mean, you need. Of course, you can. There's not the question of can you find out about it? Yes, of course you can, but it's slightly more complicated. So the key difference really here is building a distributed system versus a decentralized system. Right? There's been a tweet by the Apache Kafka Twitter account recently, like boasting and bragging and boasting about, okay, let's build a decentralized system with Apache Kafka. Yeah, well, good luck trying to do that, right? So it's not really decentralized, it's distributed, and that's different things, and that sort of implies different characteristics of the overall system that you build. The fundamental idea that's been underlying all the ideas that I've basically thrown out today is that we still want to limit, even when we build a distributed system, we still want to limit the amount of remote interaction as much as possible. Stefan Tilkoff's quote, I like monoliths so much that I'd like to build many of them, right? It's not a bad idea to really think about what are the aspects that we like about monolithic systems, and why should we throw them out of the room just because we now build or make up our overall system of, like, let's say 4 or 5 or 6 or what have you. And yeah, the other thing being that's some kind of the overarching goal that I usually try to think about when it comes to how many systems do we actually split up our system, or how do we actually structure our macro architecture or data integration. Really try to avoid having to reach out to other systems while you're serving a user request. That dramatically simplifies things a lot. Or the other way around, if you basically start talking systems left and right, then it's going to be very complicated. With that, I'd like to close. Thank you very much for your attention, guys. I will be around today up until the late afternoon. If you have questions, reach out to me on Twitter, email, what have you. It's been a pleasure. Thank you very much.